Alright, another in this series of videos, taking a look at conventional physics as taught in university by Professor Lewin, MIT, and such. And it's pretty much the same in the other places, but maybe. Yeah, they make different mistakes, my opinion.
When I expose material to an external magnetic field, then we learned last time that the field inside that material is modified. And we express that in terms of an equation that the field inside the material...
So again, this is the assumption that there's already a field inside the material, and I would argue, especially for paramagnetic, there's no poles that you're lining up. There's no little magnets inside. You're charging the atoms themselves, pressurizing them, and in doing so, creating a mirror to the field that is produced, that was influencing them. So I think a mirror is the best way to think about it. You're turning this surface into a mirror, and it's reflecting back the field you're throwing at it, and that multiplies.
Field is kappa of m, which is called the relative permeability, times the external field, and I will refer to that all the time as a vacuum field. And when we have diamagnetic material, kappa m is just a hair smaller than 1. With paramagnetic material, it is a hair larger than 1. But when we have ferromagnetic material, it can be huge. It can be 1,000, 10,000, and even higher. Now, in the case of para and ferromagnetic material, the kappa of m is the result of the fact that the intrinsic dipoles of the atoms and the molecules are going to be aligned by the external field. And today I want to raise the question, how large can the magnetic dipole moment of a single atom be? And then comes the logical question, how strong can we actually then have a field inside ferromagnetic material? That means if we...
Alright, so this is done with really, in my opinion, just kind of a lot of sloppy generalizations and stuff like that. This idea that you're going to convert the individual atoms and try to explain the magnetizing effect, the magnifying effect of the force. And I think this is just contrived. This whole way they establish that somehow this comes down to the individual atoms, when it comes down to the fact that you're doing this reflecting thing, and the reflecting thing is what's creating the well, in the case of ferromagnetics, it's a little different because you're aligning the dipoles, but in paramagnetism, no.
We're able to align all the dipole moments of all the atoms. What is the maximum that we can achieve? To calculate the magnetic dipole moment of an atom, you have to do some quantum mechanics, and that's beyond the scope of this course. And so I will derive it in a classical way, and then at the very end I will add a little pepper and salt, which is quantum mechanics, just to make the result right. But it can be done in a classical way, and it can give you a very good idea. If I have a hydrogen atom, which has a proton at the center, has a charge plus E. E is the charge of the electron, but this is the plus charge. And let this have an orbit R, circular orbit, and the electron here, E, I'll give it a minus sign to make sure that you know that it's negative. Say the electron goes around in this direction. This is the velocity of the electron. That means that, of course, the current around the proton would then be in this direction. If an electron goes like this, the current goes like that. That's just by convention. The mass of an electron, you should know that by now, is approximately 9.1 times 10 to the minus 31 kilograms. The charge of the electron, 1.6 times 10 to the minus 19 coulomb. And the radius of the orbit in a hydrogen atom, it's often called the Bohr radius, by the way, is approximately 5 times 10 to the minus 11 meters. We're going to need these numbers. That's why I write them down for you.
Right, but they're all, like I said, you could contrive it with any numbers. I could use the Dixie cup and do the same thing and say Dixie cups are a representation of, magnetic fields. So
if you look at this current running around the proton, it's really a current, which the current, say, goes in this direction, and here is that proton, trying to make you see three-dimensionally, then it creates a magnetic field in this direction, And so the magnetic dipole moment mu is up.
Right, so we don't have any evidence of any of this as being a fact, that somehow just going around the proton makes magnetism happen. Somehow this field is created, or this disturbance in the field, or however you want to look at it, as an ether thing or something, and there's these flowing fieldy thing that's going through this orbit, and there's no evidence of any of that. So this is just a representation of a piece of symbolism, but it doesn't, in my opinion, get anywhere close to the reality. And the reality really just has to do with how much of that electron is blocking how much of the proton. So it's a real fact that what the proton is excreting as a force is blocked by the electron. So if an electron's in front of a proton, it's blocking the existence of the proton. So if you have a few electrons, you can sort of understand that if they're in positions that they get closer, the closer they get to the proton, the more of that proton they're going to block. Just like, this is the inverse argument. The closer my finger gets to the camera, obviously I can black out my whole existence. And it's exactly the inverse effect for what's happening inside of atoms. But you can just get the idea that it makes a huge difference, where these things are relative to each other, how strong they are as influences. I think that as a minimum statement can be accepted by anyone.
And the magnitude of that magnetic dipole moment, as we learned last time, is simply this current I times the area A of this current loop. Now the area A is trivial to calculate. That's pi r squared, r being the radius of the orbit. And so A, that's the easiest, is pi r squared. And if I use my 5 times 10...
Again, if it was a wire circuit, this would make some sense, because the wire, how much influence that it's going to create inside the wire would be dependent on the area. So the area would give you the circumference of the thing containing the area. But doing this to an atom, in my opinion, makes no sense.
To the minus 11, then I find that this area is 8 times 10 to the minus 21 square meters. So that's easy. But now comes the question, what is I? What is the current? So now we have to do a little bit more work. And we have to combine our knowledge of 802 with our knowledge of 801. If this electron goes around, the reason why it goes around is that the proton and the electron attract each other. And so there is a force in this direction. And we know that force, that's the Coulomb force, it's an electric force. That force is this charge times this charge, so that's E squared, divided by our famous 4 pi epsilon 0,
but there's no explanation of that force at all. I mean, it's obviously attraction is hard to explain, pull is hard to explain, and they don't explain it.
Then we have to divide it by the radius squared. So that's Coulomb's law. But from 801, from Newtonian mechanics...
My obvious explanation is that they're radiating a force evenly from all directions, and the force that the electron excretes is being excreted perpendicularly out of the proton, and the electron is doing the same thing to the proton force, which means nothing reflects between them, which means there's no pressure created between them. So there's low pressure, and that's what's moving them together. Is the external pressure then pushes them into each other. Gravity.
We know that this is what we call the centripetal force that holds it in orbit, so to speak. And that is mv squared, m being the mass of the electron, v being the speed of the electron, mv squared divided by r. And so this allows me to calculate, as a first step, before we get into the current, what the velocity of this electron is. It's phenomenal. It's an incredible speed. So v then...
So this is where they'll contrive a speed for whatever circumstance they need it to be. But obviously we know that even in the standard model, these speeds are different. So this is just pull out of... Well, we need it to be this speed for the number to come out. So this is one of the variables that is just complete mush, is the speed of the electron. This clearly, we know that the speed of the electron changes depending on what current you're moving and what voltage you're at and all kinds of things. So the speed of these electrons in this state as an atom is ambiguous, and they're giving it and they're just being allowed to say, well, for this equation, it'll really work for me well if I use this number. So they're just making a number that's going to work in the equation, give them the right answer. But the number's just made up.
I lose one r, so I get the square root. I get an e squared upstairs here. My m goes downstairs. I have 4 pi epsilon 0, and I have here an r. And I know all these numbers. I know what e is, I know what capital R is, I know what 4 pi epsilon 0 is. 1 over 4 pi epsilon 0 is the famous 9 times 10 to the power 9. And so I can calculate what v is. And if I stick in the numbers, and if I did not make a mistake, then I find about 2.3 times 10 to the 6 meters per second. It's an immensely high speed, 5 million miles per hour. If this were a straight line, you would make it to the moon in 3 minutes. 5 million miles per hour. This electron goes around the proton. Now I have to go to the current. I have to find out what the current is. So the question that I'm going to ask now is, how long does it take for this electron to go around? Well, that time, capital T, is of course the circumference of my circle divided by the speed of the electron. Trivial. Even the high school students in my audience will understand that one, I hope. And so I know what 2 pi r is because I know r and I know v, and so I can calculate that time just by sticking in the numbers, and I find it is about 1.14 times 10 to the minus 16 seconds. Just imagine how small that time is. We cannot even imagine what it's like. It goes 10 to the 16 times per second around.
And again, I'd say this model was just accepted 100 years ago, that these things are moving, and they all stuck with it, but I don't think they have any evidence of any of this motion inside the atoms. I think it can be just as well modeled as magnetic positions that the electrons are in, and that they aren't flying anywhere. They're just stuck in magnetic positions.
But it has this huge speed. The 1.14 times 10 to the minus 16 really should have been 1.4 times 10 to the minus 16. Of course, it doesn't make much difference, but in case you substitute in the numbers, it is 1.4 times 10 to the minus 16. Now, we still haven't found the current that we all...
In case you actually do these equations, which no one ever really does them, their math doesn't, there's cases where, like even in the 2-slit experiment, they say this is where it's supposed to be and this is how intense it's supposed to be. And if you look at the actual pattern, it doesn't match, but they don't care.
Almost there. Because when you look here, there is this electron going by, and every 1.14 10 to the minus 16 seconds, that electron goes by. So the current I, that's the definition of current, is the charge per unit time. And so every capital T seconds, the charge E goes by, and so this is per definition the current. And so this current then, that you have, which is simply due to the electron going around the proton, is about 1.1 times 10 to the minus 3 amperes. And that is mind-boggling. A milliampere, one electron going around a proton, represents a current of a milliampere. And now, of course, I have the magnetic moment mu, that is I times A. We already calculated A, and now we also have the current I, and so we now get that mu is approximately 9.3, if you put in all the decimals correctly, times 10 to the minus 24, and the unit is, of course, amperes square meters. This is area, and this is current. This A has nothing to do with that A. This is amperes. Be careful. And this is square meters. So these are the units. And this has a name. This is called the Bohr magneton. Bohr magneton.
Right. So just, in my opinion, a contrived pile of symbolically connected stuff, but it's the wrong variables. It's the right answer for wrong reasons kind of stuff. It's just the wrong model. They've made a wrong model that has similar pieces in it, so it ends up doing the same Rube Goldberg end result, but it does it with just not how it happens in reality. It's like you could make a model for water on top of Niagara Falls and then water at the bottom of Niagara Falls. You could make lots of different models for how the water gets there, slope or straight down or this or that, and you could all end up with the same result, but it's one is going to be the truth.
What we cannot understand with our knowledge now, but you can if you ever take quantum mechanics, that the magnetic moment of all electrons in orbit can only be a multiple of this number. Nothing in between. Quantum mechanics, the word says it, it's quantization. It's not in between, it's either or. It includes even zero, which is even harder to understand, that it can even be zero. In addition to a dipole moment due to the electron going around the proton, the electron itself is a charge which spins about its own axis. And that also means that the charge is going around on the spinning scale of the electron. And that magnetic dipole moment is always this value. And
so again, more, what doesn't even make any sense? The spin of the electron is the same value as the orbit of the electron. I mean, you know, come on. It's mush.
So the net magnetic dipole moment of an atom or a molecule is now the vectorial sum of all these dipole moments, all these electrons going around, means orbital dipole moments, and you have to add these spin dipoles. Some of these pair each other out. One electron could have its dipole moment this direction and the other in this direction, and then the vectorial sum is zero. The net result is that most atoms and molecules have dipole moments which are either one Bohr magneton or two Bohr magneton. That is very common. And that's what I will need today to discuss with you how strong a field we can create if we align all those magnetic dipoles.
So just another way of saying, in a way, that you could have chemical bonds where they bond with just one electron, or they can have bonds with two electrons. And so it's got to be a multiple of electrons that are the bonds. There's no bonding with 1.5 electrons. There's no a half electron bond or some kind of crap like that. So there's other things to analogize this to. But the fact is that it really just has to do with, you can either put an electron into an orbit or not put an electron into an orbit, in terms of making changing the polarity of the atom. So if you add an electron, you're adding a mask to the proton, and you're creating an electron-heavy atom. If you subtract an electron, you're creating an electron-weak atom, and therefore it's a proton-strong atom. So that's how you're creating your monopoles. So the real questions are just about when you're making a monopole or when you're moving a dipole. And these are, something that's already exists is something that's ionized or polarized, and something you are polarizing.
The magnetic field that is produced inside a material when I expose it to an external field, that magnetic field B is the vacuum field that I can...
this was, I hate these symbols. So he's using B to describe the field inside the thing, and also B to describe the field outside the thing. So what sense can that make? If you're going to make a distinction between the source and the field, what it's excreting versus something hidden inside, they can't be the same thing. You can't use the same symbol for them, I don't think.
Create with a solenoid, we will discuss that further today, plus the field which I will call B prime, which is that magnetic field that is the result of the fact that we're going to align these dipoles. The external field wants to align these dipoles, and the degree of success.
Right, so it's only in ferromagnetic material. Again, there is no dipoles in paramagnetism. You're creating the poles. You're creating charge.
Success depends on the strength of the external field and, of course, on the temperature. If the temperature is low, it's easier to align them because there's less thermal agitation. If, and that's a big if, today you will see why it's a big if B prime is linearly proportional to B vacuum, if that is the case, today you will see that there are situations where that's not the case, then I can write down that B prime.
Well, I'd say the obvious case where it's not the case is the coiled wire. Frankly, lots of things, the wire has a tiny bit of current in it, and it creates a bunch of magnetism inside the coil because it's being reflected.
Equals psi of m, we call that last lecture the magnetic susceptibility, time B vacuum. It's a linear proportionality constant, if I can do that, because now I can write down that B is 1 plus psi m times B vacuum. And that, for that we write kappa of m times B vacuum, which is the equation that I started out with today. And so that is only a meaningful equation if the sum of the alignment of all these dipoles can be written as being linearly proportional with the external field. And this is what I want to explore today in more detail. With paramagnetic material, there is never any worry that the linearity doesn't hold. But with ferromagnetic material, that is not the case. Because with ferromagnetic material, it is relatively easy to align these dipoles because they already group in domains, as we discussed last time, and the domains flip in unison. And
So, he kind of went through paramagnetism very briefly and just said, there's no problem with this proportionality. Well, no problem with the proportionality is because the field you're getting is really a reflection of the field you're producing. So you're not producing much of a field in the paramagnetic material. You're just creating a mirror that's reflecting whatever field you're producing, and therefore whatever the strength of your field is, you're going to get it back plus, because it's going to reflect.
So with ferromagnetic material, as you will see today, we can actually go into what we call saturation, that all the dipoles are aligned in the same direction. And now the question is, how strong would that field be? I'm going to make a rough calculation that gives you a pretty good feeling for the numbers. It depends on what material you have. I will choose a material whereby the magnetic dipole moment is 2 Bohr magnetons.
So this really just has to do with how strong a magnet you can make out of how much material, and that's really all it's really saying. So whether you're making neodymium magnets, or you're making iron magnets, or you're making an electromagnet, and where you're charging, you're arranging the ferromagnetic material, the steel, turning it into a magnet by putting a coil around it. There's only so much you can get out of it. There's only so many little magnets you can make line up. There's only so many little magnets, and then there's only so much alignment you can possibly acquire. But yeah, it's going to be sort of temperature dependent again. So, superconductor magnets, of course. So cold is going to give you an advantage.
So this is, I told you it's either 1 or 2 or 3. I picked one for which it is 2. And I have them all aligned. So I take the situation that they're all aligned. So here is the current going around the nucleus. Here's another one. Here's another one. Here's another one. This is a solid material.
So this is sort of saying that, okay, when he's saying 2 Bohr magnetons, he's basically arguing in a sense that he has a double ion or something, that there's that this is like an atom that's highly polarized. It's a strong dipole, not a weak dipole. So you could have a weak dipole and a strong dipole, a 1 or a 2. And so he's using an example of material that that has in it already very strong dipoles, and so now you're aligning very strong dipoles.
So these atoms or these molecules are nicely packed, and here you see all these currents going around, and all these magnetic dipole moments are nicely aligned. And so these magnetic fields are supporting each other. And the question now is, what is the magnetic field inside here? Well, that's an easy calculation, because this really looks like a solenoid, like you have windings, and you have a current going around.
Right. Now, realistically, I don't think that has anything to do with, the atoms are all lining up this way and all spinning in the same direction and all that kind of crap. It just has to do with the fact that the atoms themselves are misshapen to be polar, to be dipoles. They already have too many electrons here, too many protons down, more protons, more electrons, and all of them are just lining up like magnets. They're just doing the compass needle thing, and they're just trying to find a comfortable place to align. But they're not aligning with their orbits all in the same. The electrons wouldn't want it that way, and the protons wouldn't want it. You can sort of figure that out, right? If I have a bunch of them flat next to each other, then all the protons are really close to each other, and all the electrons will end up being very close to each other, because they'll end up having the same path, and they'll end up being, at some point, they'll cross over each other and be right next to each other. So you could obviously say that there's no way the atoms are doing this, because the protons won't allow it, because they're all going to repel each other. They want to be far away from each other. They want to be this way, so they're the farthest away possible. They don't want to be stacked on top of each other. So this metaphor, and it's just a metaphor, these aren't facts. These are their speculation, and they should just say, we speculate that this is how it could be. These are kind of how they should say, this is stuff we made up. This isn't stuff we have any real proof of.
And you remember, or should remember, that if we have a solenoid and we run a current through a solenoid, that the magnetic field in the solenoid is mu zero. This mu zero is not this mu. This mu zero is the same one that, oh no, it's not, we don't have it on the blackboard. You notice the famous 4 pi times 10 to the minus 7. And then we have the current I, and then we have N, if that's the number of windings that we have in the solenoid, and then we have L, which is the length of the solenoid. So this is the number of windings of the solenoid per unit length, the number of windings per meter. So if we could figure out for this arrangement...
So again, that none of that would work or is applicable because, as I pointed out, the assumption for that to work is the fact that the wires have to be right next to each other, that there's no air gaps. If you create air gaps, this formula breaks right down. It doesn't work. So N and L have to be limited to the fact that the N and the L, the distance is completely filled with N's, and there's no non-N space. The wire's thick enough to fill the whole space.
What this quantity is, then we're in business. I take a material which is not unreasonable, whereby the number density of atoms, I call that capital N, written in the subscript way, is about 10 to the 29. So this is atoms or molecules, whatever may be the case, per cubic meter. That's not unreasonable. And now I have to somehow massage the mathematics so that I get in here this magnetic...
See, it's all just massage. This is just all claymation. This isn't, like I said, this is, they should just declare what it is. This is just what they make up in their model of how it works, but they don't really have any hard evidence that it can work this way. And there's clear arguments that can be made where it can't work this way. There's no way electrons and protons are lining up like pancakes.
This Bohr magneton, the two Bohr magnetons. And there are several ways of doing that. I have chosen one way, and that's the following. I take here a length of 1 meter. So this is a solenoid, and I pick only 1 meter. Would have taken 3 or 5 meters, makes no difference. I take 1 meter. And each one of these loops here has an area A. So we would agree, I hope, that the area, that the volume of this solenoid, which has a length 1 meter, that volume is A square meters times 1. And so the volume...
Well, I'll just say it again. This is such a cheat. And, this is... I should have just passed by it because this is just garbage. I mean, it just makes up how many molecules there are, atoms in the first place. Yeah, this is a 10 to the 39th. Guess what? He probably picked that number because that's what he can make this formula work with that number. I mean, it's just it's garbage.
Is A cubic meters. A times 1 meter is A cubic meters. But the number of atoms per cubic meter is 10 to the 29th. And so the number of atoms that I have in this solenoid per meter is this A times that N. So this is the number of windings, if I call this one winding, the number of windings per meter. Or you can think of it, the number of atoms per meter, the way they're lined up. And so now I am in business.
So obviously that wouldn't work because, like I said, the atoms certainly couldn't be right next to each other like the wire, so they're not going to create the internal field and they're not going to magnify the force, and none of that's going to happen.
Because this now is my N divided by L. And so I can write now mu 0 times the current I times that area A times N, which is 10 to the 29. But look now you see why I did it this way, because I times A is the magnetic dipole moment of my atoms, and that was 2 Bohr magnetons. And so this now also equals mu 0 times twice mu Bohr times N. And I'm finished, because I know what mu 0 is, and I know what mu Bohr is. We calculated that, it's still here, this number. And I know what my capital subscript N is, 10 to the 29 atoms per cubic meter. And so I just shove those numbers in my equation, and I find that this is approximately 2.3 Tesla. for the numbers that I have chosen. It's not for all materials this way, because I have adopted 2 Bohr magnetons for the magnetic dipole moment of
Yes, you conveniently just made up numbers, right? Okay, jeez, got it.
each atom, and I have adopted a density of 10 to the 29 atoms per cubic meter. And for that situation, you get 2.3 Tesla.
Understand, for a Bohr magneton, he could choose any number. He could go 1.7, 1.3, 1.2, 1 point anything. It doesn't have to be 1 or 2. It just means that each atom is either a 1 or a 2. It doesn't mean that the whole collection of them would average to 2 or just 1. The whole collection can average to 1.3. So he could have picked any number. Any one of these variables he could change without anyone noticing that that's not right, or that's not right. So they're all just made up numbers.
Now, I want to use this number and understand what's going to happen in ferromagnetic material. I take ferromagnetic material and I expose it to an external field. I call it a vacuum field. So I stick it in a solenoid and I can choose the current through my solenoid.
I just don't know why this vacuum field thing. Why is it crawling inside a coil, a vacuum field? It's the field you're creating. It's not a vacuum field, whatever the hell that is. I hate this rhetoric.
And I'm going to plot for you the vacuum field. This vacuum field is linearly proportional to the current through my solenoid. This is an actual physical solenoid. I have a wire that goes around like this. I don't have one here now. And I run a current through there. And that vacuum B field equals mu 0 times I times n divided by L, except that this n divided by L is now the number of windings of my current wire, and this is the length of my solenoid. So don't confuse it with the one we had there, because that was on an atomic scale.
And again, it has built into it the assumption that your wire is, and your loops are enough to cover all the space. So you don't leave empty spaces between the wires. If you leave empty spaces between the wires, these numbers, this equation will not work.
And this is on a microscopic scale. How many windings you have could be, we had a big one here in class, 2800 windings, and we had 60 centimeters long, and so that's what this number is all about. So the moment that I know what the current is through my solenoid, I immediately know what my vacuum field is, one-to-one correspondence. And now I'm going to measure inside the ferromagnetic material, which I stick in the solenoid. I'm going to measure there the magnetic field. And what's going to happen now? Well, first of all, I cannot at all plot this curve on a one-to-one scale. The reason being that kappa of m for ferromagnetic material is so large, let us adopt for now a number of 1,000, say. Or could be larger even. Let's say kappa of m is 1,000. That means that if the magnetic field in terms of a vector is this big, 1 centimeter in the length of the vector, that the field inside the ferromagnetic material is 1,000 times higher.
So obviously, just a coiled wire, a solenoid, doesn't make much of a magnet. You can't pick anything up with it. You can't do anything with it. Put a nail inside of it, it's 1,000 times more magnetic. So that's all this is saying. So yeah, he wants to chart the two, and he's saying, well, look, this is the field it would be without the ferromagnetic material, and yeah, this, you know, off the screen is where what happens when you put a nail in there. But that's all he's saying. This isn't as complicated as making it sound.
If this is 1 centimeter in length, 1,000 times higher is 10 meters. So this is the length of the vector of the magnetic field inside the ferromagnetic material. That's why I cannot do it to scale.
Well, that was more than 10 meters, I'm pretty sure.
So when I draw this line here, keep in mind that if I did it to scale, if I did, but I can't, then the tangent of alpha would be kappa of m, which in this case would be 10 to the third. And so this angle alpha is something like 89.9 something degrees. So I cannot do it to scale, keep that in mind.
Then why bother doing it? What's the point? Just point out that the increase is 1,000 times, and just show anything. You could show a dot and then another dot. Say this dot's 1,000 times bigger than this dot. See, that's how big a difference there is. I think anybody can get it if you just say it's 1,000 times bigger. So it's like an elephant made out of 1,000 elephants. That's a really big elephant.
So in the beginning I get a nice linear curve, but now slowly I'm beginning to reach saturation, that all these dipoles are going to be aligned, and what you're going to see is that this curve bends over and bends over and bends over, and the magnetic field that you finally achieve here is the famous 2.3 Tesla, which I calculated for that imaginary machine.
Yeah, but you didn't calculate anything. But yes, just clearly you're putting you have this reflecting enclosed magnetic field stuck, can't get out. And you stick a ferromagnetic material in, and yes, it's going to align every single magnet, all of them, because it's a strong field inside, and make a magnet out of it. Okay, but that's it.
Material plus B vacuum. The 2.3 is now the field which I will call B prime. This is the field that is the result of the alignment of all those dipoles. And so when I increase the vacuum field, this goes into saturation and settles for 2.3 and can no longer increase because I have aligned all these magnetic dipoles. And so if your vacuum field is this strong, then this field is no longer 1,000 times stronger than the vacuum field. You're no longer in the linear part. So you could also think of it as kappa of m being smaller than 1,000. Whichever way you prefer is fine. But it's no longer proportional to the value of 1,000.
So the catch is this is going to become important when you start using alternating current, or because there's obviously some lag time, and so you won't be able to get the same intensity as you alternate.
The temperature is lower of the material, it's easier to align them, and so you will achieve saturation earlier, and so your curve will go like this. So the curve is also a function of temperature. So this is if the temperature is low relative to this one. So these curves depend on temperature as well. The lower the temperature, the easier it is to align them. If I reach this point here, when my B prime goes into saturation, I can only increase the field, the B field in the material, by increasing the vacuum field, because B prime is not going to go up again. And so I can only get a higher field by increasing this current so that this V vacuum goes up. And that goes up very slowly because this huge magnification factor of 1,000 is gone now. So the slow is very slow, the growth, and that's why you see that I drew it like this, that it increases very slowly, but my plot is not to scale anyhow. Now I want to discuss with you what happens with the material once I have driven it into saturation. What happens if now I change the current and I make my vacuum field 0 again? And now you get a very unusual behavior. Let me do that here on the blackboard. So I make a new drawing. I could have continued with that one, but let me make a new one. So I'm going to do the following experiment in my head. I have a solenoid, and I run a current through that solenoid. And if the current is in clockwise direction, my vacuum field will be in this direction. And when the current is in counterclockwise direction, I will assume that my vacuum field is in this direction.
Yeah, when you reverse the polarity of the ballot, it's really voltage, it's not current, but whatever. It's the direction of the voltage, but who cares?
So there is ferromagnetic material in here. If the current flows in clockwise direction, the vacuum field is in this direction. If I run it in counterclockwise direction, the vacuum field is in that direction. And here is going to be my vacuum field. It's easy for me to know what that is, because if I know the current through my solenoid, this equation will immediately tell me what the vacuum field is. So I've never any problems with the vacuum field. I stick a probe in here, and I measure the magnetic field inside that material. How we do that is not so easy, but we can do it. There are a few things that I can't tell you. This is one of them.
Yeah, I can't tell you. It's a special radar they use or something. Yes, but I'm sure, whatever. Measuring inside is, again, just measuring voltage, essentially. Fields inside materials are not the same. It's the same energy, but it's in such a distinctly different form, in the sense that it's caught inside the atoms. You can't really, the pressures inside the atoms are bumping into each other, exchanging pressure. That's not exactly the same thing as radiating it.
So here is a magnetic field inside the material. All right, so there we start. We do the same thing that we did here. So we approach the saturation. But now when I'm here, I am reducing the current and go back to zero. Remember that when we are here, all these domains that we discussed last time have all flipped in the direction of the vacuum field. So this field is enormous. But now I make the current go back to zero.
All right, by making it go back to zero is not as threatening as reversing it. So the point is now you've arranged them. They're probably, a lot of them are going to stay in their new arrangement because they don't like moving anyway. So some of them are going to stay there. But, you know, what percentage, 75% or whatever. And now if you reverse the field, then they're screwed. Then you're going to reverse. You're going to lose everything you created. But once you've created the domain alignment, it has some permanence. Wrong way to say. I mean, it has some rigidity, but it's not strong. But it's there. So you have to agitate it or force it to fuck up or to lose what you've given it. It's probably a good way to say this, but yeah, I mean, it's sort of like giving something a momentum. It's going to keep it, but you know, if it hits something, it's going to lose it.
And what happens now is I end up here, at this point P here. The current now is zero. There is no current going through the solenoids. Notice the vacuum field is zero. I can take the material out, the ferromagnetic material. The material itself is now magnetic. And you see,
but you also have to remember that coil had that capacity to sort of create its own, like a capacitor, it's storing energy, and some of that is still there too. So there's not a huge, the inductance isn't going to go to zero, which you've induced in the coil immediately. So that's another part of the reason why the ferromagnetic material doesn't immediately fall apart, is because the induced field still exists.
there is a magnetic field inside it. Why is that? Because some of those domains remain aligned. They don't go back. And so we have created permanent magnetism. And so in the location, at the location P, we have B vacuum is zero, but B prime, which is the result of those aligned magnetic moments, is still in this direction. Nothing is to scale here, of course.
So this is just problem with the semantics. Is, you know, he said we've created permanent magnetism. I've used the word. I mean, these aren't perfect words to use because it's not permanent in any hard sense. It can be permanent in a hugely variable sense in terms of how fragile the magnetic structure is and how easy it would be to get rid of it. You could just tap it with your finger. You might have to heat it. It could be in all kinds of different states of rigidity. You know, so it's calling it permanent is, you know, not very good, not very precise. So it's just, I mean, it's not his fault. It's just we don't have enough words in our vocabulary.
And so you still have a magnetic field. Now I reverse the current. I go counterclockwise. So I'm creating a magnetic field vacuum now in this direction. And so now what will happen with this curve? I come up here. And look now here, at this location Q. What do I have now? I have something very bizarre. I have now a situation whereby the vacuum field is in this direction, but there is no magnetic field inside the material. The magnetic field inside is zero. So when we have point Q, so we have B vacuum is in this direction, but B inside, B prime, oh no, it's not B prime, it's B. It's the total field inside is zero.
Right, so the total field, it just means that now you're still in the conflict stage. You have some parts of the magnet that you made kind of rigid going one way. Now you're turning half of the magnet going the other way. So now you have two different magnets. And so now they're fighting each other, so to speak. And the end result is no magnetism. So you're just creating some field, and it comes out to no field. But there's not no field. It's just that the fields are consuming each other.
The reason being that B prime is still in this direction.
Again, wrong word to use. They don't consume each other. If you're creating black and red, and so you had a point where you were making more red go one way and more black go the other way. So you've taken some black from going this way and sent it over this way, and some red this way going over this way. So you've changed the percentage, 60-40, 60-40. And now you're changing it. So now you're turning it back into 50-50. Okay? Because half of the things are going to be saying, yeah, I got 60-40 going this way, and half are going to be 60-40 that way. So they're going to be doing the opposite thing, and the net effect is 50-50.
The reason being that the domains are still aligned in this direction. And so the vacuum field plus the B prime field, which has to be vectorially added, adds up with a net field 0. Quite bizarre, isn't it? Now I increase the current, but I keep going counterclockwise. And so the magnetic field of the vacuum remains in this direction. I go into saturation again, in a similar way that I went into saturation here. And now I stop here.
So those are the only two real points of the saturation point. These other points will never really be experienced for any length of time. So, they don't really count that much.
I don't want to lose my brooch. And now I stop here and I say to the current, go back to 0 again. So,
I mean, they only matter if you're creating high frequency. So the higher the frequency goes, the more this thing breaks down, because there's not enough room for the width time thing to happen. So you'll never get to saturation points.
So my current now goes back to 0. There we go. And now I arrive here, point S. And again I have a situation that my vacuum field is 0. I could take the material out of the solenoid, just walk around with it on the street, it will be a permanent magnet. But now the magnetic field inside this material in point P, it was in this direction. If I take it out here, then it is in this direction. Now some domains stay aligned in this direction. The reason was that I had counterclockwise current, and so those domains flipped over. And they're not all willing to flip back again. So I've also made a permanent magnet here. Vacuum field.
Yeah, much weaker than it will be when you go much weaker than if you stayed at saturation without reversing the current.
0, but B prime is now the opposite direction. And then, if I continue now to go clockwise with current again and increase the current, I end up there. And this is a bizarre curve. We call this the hysteresis curve. If you look at this curve, it's really amazing. It's actually hard to digest this. You have to give it a little bit of thought.
They really don't. There's mechanical things you could probably compare it to in terms of anything that has momentum goes through these transitions where the momentum has to be eaten up before it can go back the other way, and then it slowly goes back the other way, and then it reaches its maximum and peak again, and it goes through the same process of transferring the momentum. So that's sort of all you're doing. It's sort of just a transfer of momentum.
Because for one particular value of the current, for instance, here, once I have a particular value of the current, I know that B vacuum is a given. I have two possibilities here for the magnetic field. And for the current here, I have two possibilities for the magnetic field. And so I cannot even know when I take this material and I expose it to an external field, I can't even calculate what the magnetic field inside will be. It depends on the history of this.
Yeah, it depends on what the last current was you put through it. So if you're alternating current, obviously, if the last current was going this way, then that's what kind of magnet you're going to have. If the last current was going this way, well, then that's the kind of magnet you're going to have. Not that challenging. But anyway, I think we'll stop here and call it a video and such. So, till the next time and such.